Stefan? Oder Georg? Habe ich denn jetzt nichts hier? Stefan, hörst du mich? Was ist das denn jetzt?
Also Wolfram, ich höre dich gut.
Ja, ich auch.
Okay.
Und Stream hat auch Audio. Einfach verzögert um 1 Minute oder so.
Na gut. Okay, I think, let's see, I should share now. Okay, so let's start. Good afternoon, everybody. So last time we talked about diodes, and I think we will skip the last part about the photodiodes and jump directly to transistors, also for the benefit of those who start doing practical exercises with transistors today. So the word transistor is an artificial word. It stands for transfer resistor because it's somehow a resistor that is controlled by an external voltage, or it can also be viewed as a controlled current source. So basically with one terminal we can control the current that flows through the device, and we'll see later how that works. And this is then the basic for a lot of things like signal amplification, analog control of devices, but also digital logic, although today these transistors, the type of transistors that we discussed today, is not used for digital logic anymore. So today we'll talk about the bipolar junction transistor, or BJT. And in 2 weeks or so, we start talking about the field effect transistor, which is today applied mostly in digital logic, but also some analog applications. And historically, the transistors were vacuum tubes or valves. So the structure of a bipolar transistor is shown here. It's like the connection of two PN diodes with opposite polarity. So we have a P region, an N region, and a P region again. And the middle N region, in this case, for a so-called PNP transistor, is called the base. So you can, in some sense, view it as this kind of arrangement of a diode where the direction of where it passes current is towards the base from this side, and also towards the base from this side. Now, when we operate it, usually the left diode is in forward bias, so the current flows from this terminal into the base, while the right-hand side diode is always operated in reverse bias, so there would be no current flowing here. However, this obviously, when you really do it with two discrete diodes, will not do anything. So two separate diodes are not a transistor. The transistor action only shows up when you actually join these regions. And so we'll look at that now. So if you have the left bias, the left PN diode here, which is operated in a forward bias, you can look at the band diagram here. So so here you have a reduced barrier height, and there will be charge injection or carrier injection from the base into the P region here, for instance. So electrons from the N region are injected across the reduced barrier height into the P region, and holes from the P region are injected from the P region across the reduced barrier into the base. So this is called minority carrier injection, because then when they reach the base, they are minority carriers, or when the electron reach the P region, they're minority carriers. Well, of course, here they are the majority carriers. So this gives rise to these large forward current with this exponential behavior that we've seen in the diode last week, and the current is sustained then by recombination. So the injected charges recombine, and far away from the junction we have the equilibrium densities. On the other side, the diode is in reverse bias, so the barrier height is larger than the equilibrium value, so there's no injection across this increased barrier. But whatever carrier does his random walk into this junction region here, into the field region, will be swept away by the field, and that gives rise to the small reverse current that we know from the diode. Now we bring the two things together and look at the electron current first. So the N regions of these two diodes joined together are the so-called base, and here we still have the same electron injection coming from the base into the left P region. The current, of course, goes in the opposite direction because the electrons are negatively charged. So that doesn't change very much, and we, from now on, will most of the time neglect the reverse current due to the electrons, which is here. Now, if you look at the holes instead, we also have the injection of the holes across the reduced barrier height into the base, but now there'll be the recombination here will be negligible. Instead, the holes fill the whole base, which is thought of as narrow. So there's not enough room, not enough length for them to recombine, and they basically go through this narrow base. And on the other side, the junction field sweeps away all the holes that arrive here. It's like a vacuum pump that sucks the holes out of the base here and makes sure that the density of holes goes to zero at this point. So we have a very strong gradient here of hole density across the base, which maintains a very strong diffusion current, which in turn gives us a very strong injection again. Like I already said, we can neglect the recombination here in most cases. So what we have now is a strong diffusion current of holes and a small diffusion current of electrons. So this is now a three-terminal device. The base current for the electrons has the usual PN diode characteristics, which is given by this formula, e to the VEB. So VEB is the voltage between the emitter and the base, divided by the thermal voltage minus 1. And there's a much higher current of holes that flows directly from this P region, which is hence called the emitter, because it emits the holes to the collector. So this is the important current for us. For the PNP, it's a hole current. It flows from the emitter to the collector, and hence the names of these terminals. Now, base and collector current depend on the same base emitter voltage on this barrier height in the same way, and that means that the base and the collector current are proportional to each other. So this is interesting because now we have a device, this box here, that in which one terminal, the base, controls the current between two others. So this is like no other thing that we've looked at so far, where always the voltages at the terminals control the currents that went into those terminals. Here we have control over the current between two other terminals. And this can be then used as an electronic switch or as an amplifier, as we already said. Okay, so let's look at the characteristics of such a transistor. First, we start with the collector and base currents as a function of the base emitter voltage. So we have a forward biased emitter base diode here, and we plot here as a function of the voltage that we apply the base current and the collector current. And so they both have this exponential shape that you expect for a diode. And the collector current is a large factor higher than the base current, but otherwise has the same shape. So the collector current here is, however, a very steep function of this emitter base voltage. That makes it difficult to control the collector current directly using the base emitter voltage, because here you have very small changes that cause huge changes in this current. This can, however, still be used as an amplifier, and we'll see examples of how that is done. However, in sometimes this argument is turned around, as we also did with the diode, to say that in whatever circuit I build, the voltage between emitter and base is always of the order of 0.6 or 0.7 volts. We haven't talked about the role of the collector potential. So far in this plot, only the base emitter voltage shows up, and we haven't talked about the collector. We just said that it's in reverse bias here, and the field collects the injected holes. Now let's take a look a bit in detail how it does that. So as long as there's a junction field here, so when there's no base collector voltage or a positive base collector voltage, the field, the junction field is here, or even higher when we increase the base collector voltage. This field collects the holes that diffuse into the base. We neglect the reverse current here, and the current is then independent of what the base collector voltage is. It doesn't really matter. We already collect all holes when this potential is more or less at the same level as this one. There's still a junction field. However, if we go to a negative external base collector voltage, then we will start seeing a non-negligible diffusion current from the collector into the base. So the barrier here is being reduced. So there is still a built-in field which collects the holes, so the current in this direction continues, but there is an increasing current in this direction as well, which starts to counteract and the current in this direction. So in this configuration, then both junctions start flooding the base with holes. And this is called the saturation, because the base is saturated with holes. So we have two regions of operation here: the active region, where the collector voltage is below the base potential, and we start getting into the saturation mode, where the collector voltage is coming close to the base voltage. If we include all of these currents, so the diffusion from the left and the diffusion from the right, then the collector current changes from the well-known diode formula that we had before. It gets a second diode basically that describes the current from this side, although with a slightly different factor in front of it, because the transistor is not completely symmetric typically. And this is called the Ebers-Moll equation. There are several Ebers-Moll equations. There's one for the base current and one for the emitter current as well. So this describes the full behavior over all possible voltages. And however, we will restrict most of the time to the active region, and then only this term here is important, and the bias of the base collector voltage is such that we can neglect this term here. So what does it look like now? If we plot the collector current versus the base collector voltage for different values of the base emitter current. So if we go to large positive values of the base collector voltage, then the collector current becomes constant. This is the active region, and then as we go in the other direction, when we go more towards forward biasing the collector base diode, there's the current in the other direction, which starts to compensate the forward current, and the current goes to zero. It can even go in the other direction. So in principle, you can operate a transistor, of course, in both in both directions. So the roles of emitter and collector can interchange. In practice, that's not the case because these devices are never physically symmetric. So we'll focus on the forward direction, which is this here. Now, if you increase the emitter base voltage, that just increases the current that flows here. So this curve will go upwards. So now we're plotting this versus the base collector voltage. And like I said, when we're in positive base collector voltage, this is called the active region, and negative base collector voltage, we start getting into saturation. What is more common is to plot this not versus the base collector voltage, but versus the emitter collector voltage. And this is done here. So we don't look at the base collector, but the emitter collector voltage, and now we get this set of curves. So the border between saturation and active is now not a constant, a vertical line here. It moves a little bit, but in principle you still have on the right-hand side your active region where the current becomes independent of the emitter collector voltage, and here you get into saturation and the current drops to zero, although we still have a positive base emitter voltage. So this is then showing the whole thing in terms of a circuit diagram. So this is the symbol for a diode, and we apply a voltage between the base and the emitter here, and the voltage between the collector and the emitter here. So the control voltage is VBE, and in the active region we expect this exponential behavior of the current versus this base emitter voltage. And same now for the NPN transistor. So you can interchange N for P, and then the current now is an electron current that flows from the emitter to the collector. The control voltage is still the same, but with a different sign. So now the emitter has to be positive with respect, the base has to be positive with respect to the emitter, and the collector also has to be positive with respect to the emitter. While in the previous case, when we looked at the PNP transistor, the emitter was the most positive node, and the collector was more negative. But other than that, the two transistors work in the same way, and we'll look at different ways of using that. Okay, so now what does a real transistor look like? They are mostly not put together by blocks of silicon like the diagram suggested that we've used, but they're fabricated in so-called planar technology. So one takes like a disk of material. Here, for instance, for a PNP transistor, you can take a disk of or a wafer of P-type material in which you embed then an N region, and inside the N region you put another P region, and then the transistor action is basically happening here. So you have the emitter, which emits the holes. In this case, they go through the N-dope base then into the P region. Then in this case, the collector would be connected from the back side, but sometimes the connection can also be made on the side from the front side. What you see immediately is that these are geometrically not symmetric. So real transistors do not have the symmetry between NPN that the drawing, do not have the symmetry between collector and emitter that the drawings on the previous pages suggested, but they're physically very different, and then that's why they work much better in one direction than in the other direction. So you can get these transistors in different packages. So most common are these plastic packages. When you have low power transistors, if you have a little more power to dissipate, then these metal cans are more suitable. Or if you have high power transistors, then there's usually also a heatsink attached to it. And this is a photo of a surface mount transistors, which are very small. They all have in common that they have these 3 pins, and usually you have to look into the data sheet to find out which one is the base and the emitter and the collector. Okay, so let's look at the characteristics now of one typical transistor. So this is the 2N222, which is a very commonly used NPN transistor, general purpose transistor. So the collector emitter voltage for this one must be less than 40 volts, and the collector current less than 800 milliamps. So these type of transistors are usually operated with a few volts and a few milliamps. But there are also transistors that can work for substantially higher currents and voltages, but then they have bigger packages, of course. These are more specialized transistors. So this plot here shows the collector current as a function of the collector emitter voltage, where the base emitter voltage was varied in steps of 20 millivolts. And you see the same curve that we discussed previously. So it rises quickly in the so-called saturation region, and then becomes constant in the linear region. Now, unfortunately, the naming of these regions for the other type of transistor that we'll come back to later is unfortunately just the opposite. This one will be called the saturation region, just to confuse you. But here this is called the saturation region because the base is saturated with carriers here. And we are mostly interested in this linear or active region here. So what you also see is that the distance of these curves is not equidistant here because we go in constant steps of the base emitter voltage, and since the collector current is a steep function of the base emitter voltage, these distances are not linear. So with very small base potentials, here we can make the collector current change over a very wide range, and in the end you will end up in your circuit always in a more or less in a small region around 0.7 volts. Here's another plot showing something similar. Now we vary, instead of the base emitter voltage, we vary the base current in constant steps, in this case of 50 microamps. And you can see that the collector current in the active region now rises in constant steps. So it's directly proportional to the base current, and the current gain for this transistor is about 200, which is a fairly typical value for this bipolar transistor. What you can also see here is that the current is not exactly independent of the collector emitter voltage for a real transistor, but only approximately. But it's in quite good approximation constant. So this transistor is a good current source, or a current sink in this case, because here the current flows into the collector. If you want a current source which sources current, then you need a PNP transistor. So the bipolar transistor can be seen as a controlled current source because the base current and the collector current are always proportional to each other. The constant of proportionality is called beta, or sometimes HFE. This is the ratio of the two currents. Strictly speaking, beta is the derivative of the collector current with respect to the base current, but we will not make this distinction here most of the time. So in most of the cases for bipolar transistors, you have values between 30 and 300. If it goes below 30, then it's not really a good transistor anymore. But for these high values, the base current is small enough to make this an excellent amplifier. There are some transistors available that have even higher, in the thousands, but these use then slightly different technologies. Typically, the current amplification for NPN transistors is higher than for PNP transistors because of the mobility or the diffusion constant of electrons, which is much higher, or 3 times higher than the mobility for holes. So the diffusion through the base leads to much higher currents for NPN transistors. So often NPN transistors are preferred. So there's this nice equivalent circuit here from Horowitz and Hill. So in this active region, you can think of your transistor as a diode where the current flows in here, and there's a man inside the transistor man inside the transistor which checks this current and makes sure that through the other terminal a multiple HFE or beta flows. A word of caution is that one cannot really rely on the value of HFE, so there are or beta. There are large variations among transistors of the same type, so it depends on many small things. And so this histogram shows a distribution of beta measured for one type of transistor. So these are all the same from the same box, so to speak. But if you measure the amplification, it varies quite a bit. But it also varies with temperature and the collector current itself. So it's only approximately constant. And if you design a precision circuit, then it should not rely on the exact value. And we will see how to do that later. On the previous plots, you've seen here that that this current was not exactly constant, but it grows very slowly with the collector emitter voltage, which we don't expect, because the current collection is, of course, fully efficient as long as there's a junction field. And the reason why this is that the base collector junction is operated in reverse bias. So there's a depletion region between the collector and the base, and the size of this depletion region grows with growing the collector emitter voltage. So maybe remember this from the diode, where we also saw this growing depletion region, which was, for instance, used in this varactor diodes, where the capacitance of this depletion region was varied by varying the voltage across it. But now, if the depletion region here between the collector and the base grows, that means that the effective width of the base becomes smaller, because this depletion region starts eating into the base. And since the current, the diffusion current, is proportional to 1 over the width, that means that our collector voltage is not exactly constant, but it grows with the collector emitter voltage. So this is called the effect of changing the width of the base is called base width modulation, and this leads to the so-called early effect, which is the change of the current. So why does the current depend like 1 over the width of the base? That's because it's a diffusion current. So if you look at the density gradient in the base, then it's basically the density of charges injected on one side, which from the emitter, which is proportional to this exponential factor and the doping, more or less. And then on the other side of the base, we have this field that sweeps away the charges, and here the density is basically 0, because all the charges are absorbed. So the gradient is then of course becoming steeper when you reduce the length of this base, and a steeper gradient means higher diffusion current. So this is the analogy here is, again, if you think of the vapor, so you have a certain vapor pressure on one side of the base, and then on the other side you have this pump, and the longer you make this the path between the vapor reservoir and the pump, the lower the current of vapor that's going through here. So we have a small dependence of the collector current on the collector emitter voltage. Though this is shown here a little bit exaggerated. Usually it's much less than that, as you've seen before. And it turns out that the slope here is proportional to the current, so you can more or less draw straight lines, tangents to this curve, and they all meet in the same spot. And the place where they meet is called the early voltage, and for typical transistors, this is of the order of 100 volts or 50 volts or something like that. So phenomenologically, one writes the current now as the collector current as beta times this diode factor multiplied by this term here that describes the linear increase of the collector emitter voltage, of the current with the collector emitter voltage divided by this early voltage here. Okay, so now let's start looking at circuits with transistors. We look at the symbols first. So this is the symbol of an NPN transistor. We have the collector and the base and the emitter. And the emitter in the symbol is always marked by this arrow. So the letters are usually not found in circuit diagrams, so you have to see where the little arrow is, and that shows you the base emitter diode. So the arrow is oriented just like a normal diode would be. It indicates the direction of a positive current. So a positive current here would flow out of the emitter for this NPN transistor. So like we've seen in the NPN transistor, the base emits negative electrons. So for the PNP transistor, the base emits positive holes. So here, sorry, that's not wrong. The emitter emits positive holes. So here we have the flow of positive holes along this arrow sign, and here the current flows against the arrow sign because we have electrons that are being emitted from the emitter. The preferred orientation of the symbols is always like this, so that the current flows from the top to the bottom. So in this case, from the collector to the emitter, and from the PNP from the emitter to the collector. So if you stick to this rule, then it'll be easier to understand diagrams. However, this is unfortunately not always the case. So not everybody does it that way, and sometimes it's not even possible. Sometimes it's not clear at the time you design a circuit what the direction of currents will exactly be. So to be sure, you have to look at the arrow direction here to know which type of transistor it is, and not at the arrow position. So normally the arrow would be here at the top for a PNP and at the bottom for an NPN. But that's not guaranteed, so you also have to look at the direction of the arrow. But when you operate these transistors, normally then for the NPN transistor, the emitter should always be the most negative node, and the collector should always be the most negative node for the PNP transistor. Yes. Okay. So let's start looking at some example applications before we start analyzing a circuit with transistors in more detail. So let's look at a transistor used for switching a load, like a lamp or some other device. We have a digital signal that switches between 0 and the supply voltage, and we want to use it to turn on a load. So when the input voltage here, which can be the output of some computer, for instance, is 0, then this PNP transistor when it's high. So when this node is at the supply voltage, then this one is high. So we have no voltage across the base emitter diode, and this transistor is off. So this means that the collector current is 0, and the collector emitter voltage is the full value of the supply voltage. So in this diagram, we would be here. So let's say that our supply voltage is 5 volts, and the transistor is off. Then you end up in this region of your characteristics. Now, if you start to turn on the transistor by setting V into 0, so we're pulling this resistor now down to ground. So that means we'll have a current that can flow out of the base. So we have a base current now, which is given roughly by the difference of this supply voltage minus the diode drop here, the 0.7 volts, divided by the resistor. For instance, if you have a 5 volt supply and a 10K resistor, so you'll have 430 microamp base current here flowing through the resistor. Which means that in this situation, the transistor will try to send a current of beta times the base current, or if, for instance, this is a transistor with a beta of 70, it'll send a collector current of 30 milliamps out. So what happens is you jump here, so the transistor starts sending out 30 milliamps of current through the load. Now this will then give rise to an increase of the voltage across the load. If it's a resistor, it will be proportional to the current. If it's something else, whatever the IV curve of this load is. So the collector potential goes up, and the collector emitter voltage here, so the voltage across the transistor will reduce. So we're going down this curve in this direction, but the current will stay approximately constant, at least for a while. So if the load current is less than these 30 milliamps, sorry, if the load current is higher than, what do I say here? Yes, no, if the load current is less than that, we'll actually go down here because we don't want the transistor is sending too much current. And the load doesn't take it, so the voltage here will go so high that the current through the transistor goes down again. So we're driving this transistor into saturation. So we're basically falling down this curve here, and if the load current, for instance, is 10 milliamp, it'll end up in this region. So here we now left the active region, went into saturation, and we have a very small voltage across the collector emitted. Which means that the load basically sees the full supply voltage, and this is what we wanted here. So now we're in the on state of the circuit. So the load voltage is almost the full supply. We have a very small emitter collector voltage, and the collector current is now not ruled by the transistor because it's not in the active region anymore, but it is whatever the load draws. So now we have so this is now really the behavior of the switch. Now you may wonder why we've done it like this. So you may want to do the same thing with an NPN transistor. However, the behavior of this circuit would be completely different. If you put an NPN transistor here, it would still be off when you set. So it would be off when you put the input voltage to 0. So you put this node to 0, and which means you pull down the base here, and then there would be also a low emitter voltage, no current through the load, and this thing is off. Now, if you turn it on, so you pull the input voltage high, then you would initially see a very large base current here, similar to the situation that we had before. But now, since the load is connected to the emitter and not to the collector, the rising voltage across the load starts reducing the base emitter voltage. So if this goes close to 5 volts here now, our base emitter voltage starts to decrease, and the current decreases too. And at some point, it reaches an equilibrium, and this point will never go up to the full load. Okay, this is also an interesting circuit, but it's not a switch. It will end up in some kind of in a situation where the load is not completely turned on, and the controlling voltage here is not the full voltage, but it is very small. So we're in the lower region of the curve. We later see a very similar circuit without these resistors, which is actually very useful, but it's not used as a switch. If you want to do switching with an NPN transistor, then you need to put the transistor below the load. So this is shown here in this configuration. So where the load is connected to the collector and not the emitter, then whatever the load does not affect the potential difference between the base and the emitter, and then it is a perfect switch again. So this is completely analogous to the PNP switch. Now, why do we use a transistor here at all? Why don't we connect the load directly to this input voltage? We could do that if the signal source was able to provide the full current that the load needs to operate. But often we want to switch loads that use relatively large currents and use a feeble voltage source here, like for instance the output of a computer. Then you cannot do it, and you need this transistor to amplify the currents that are flowing here so that a small current output from your signal source can drive a rather hefty load. Typically for these applications, the NPN transistors are slightly better than the PNP transistors because they have higher current amplification, but what you use depends on whether you need the load reference to ground or reference to the supply voltage. I should also say that the other type of transistor that we're going to see is often the better choice because it has no base current at all. But you could do it, and it is often done with bipolar transistors. Okay, so the next example we look at is now not going to use the mode where we drive the transistor into saturation, but we stay into in the active region, like we will for basically all circuits that we look at from now on. So instead of just switching on and off, we want to control the load current. So we have a current source that sets the base current. So the base current flows into the base and then out the emitter again, and it controls proportional current that flows into the collector. And this current will, of course, then have to flow through this load here. And there will then be a voltage drop across the load here. So if this point is fixed, that means that this point will go up and down. But since we are at the collector and the dependence of the current on the collector voltage is very small, this will work. So this circuit will define the current in our load over a very wide range of voltage drops across this load. So it doesn't matter very much what kind of load we have here, or whether it changes over time or with some other parameters. The current will always be the same as long as you don't go into this saturation regime. So for now we assume that we stay into this active region here, and then the current is independent of whatever load you attach here. So we have a nice controlled current source. And if we change now the base current, so we can program this, then the collector current will change accordingly. What this means is that the collector potential will move around depending on what the load here does, and you get this load curve here, but the current is always nicely proportional to the input current. So this is a real nice current amplifier or controlled current source, if you wish. This mode now can also be then used, of course, if you look at this here, the blue points, they represent a changing voltage. So you can also use this as a current to voltage amplifier, because the potential here changes as a function of this current in a basically linear fashion, because it is a good current source. If we put a resistor here, and this is a nice current controlled voltage then. You can also, again, do the same thing with the PNP transistor. So this is the NPN transistor, the emitter going away from the base. Now here we have the PNP transistor, so the arrow going towards the transistor. Now the base current goes in the other direction, so it flows out of the base, and the collector is here at the bottom, so this will control a load that is now referenced to ground. So if you want this type of configuration, with the load working towards ground, then you need to use a PNP transistor. If it's okay that your load works through the positive supply rail, then you can use an NPN transistor. Okay, I think we take a break now and then come back in 15 minutes and look at the last example and then the emitter follower circuit. Okay, so welcome back. We continue with transistors, and as the next example, we'll discuss the use of transistors for regulating power or regulating voltages. And here's an example that is actually used very often, usually as part of package regulators, like the one that you will use in your project. They have an input voltage and a regulated output voltage and some ground terminal. And then usually they have an internal reference voltage, and then the output voltage is then always defined by this reference voltage. And the way this works is like this. It needs a differential amplifier or a difference amplifier. We'll look at these in detail later. Basically, they look at two voltages, in this case the reference voltage and the measurement and the output voltage in this case, and then create an output that is proportional to this difference. And in this way, they operate this transistor like a valve. So that means if this voltage falls too low, this amplifier opens the valve here, and more current flows through until the voltage goes back up again, and we get the desired voltage here at this node. So these packaged package regulators typically have the reference already built inside. So that would be like this part here plus the internal reference. One can do something similar without this amplifier even. To see that, we now look at an NPN transistor with a fixed base potential. So we have a similar situation like before, but we're not feeding a constant current into the base, but we hold it at a constant voltage. This voltage holds the transistor, the base, and that means that we don't fix the current, but the current is determined by the voltage difference between between the base and the collector. So now let's look at this here. So this is a plot of the output voltage on this axis, and the emitter current on the other axis. And the base emitter voltage is now the difference between the reference, which is, let's say, 2.5 volts in this case, and the emitter. So the diode curve that we've seen now looks like reflected. So it's, if we go away from the reference voltage, then the current shoots up. So if you go down with the emitter, then the current that flows through the collector from the collector to the emitter shoots up exponentially. So we get this kind of curve here. Now, sorry. If on the other hand, this output voltage reflects the voltage drop across the load, and this is shown here for different types of loads. So a straight line would be a resistor. So here, this is a small resistor where a large resistor where a large voltage drop causes a small current. And here we have a smaller resistor where a large voltage drop or large output voltage causes a large current. But you can also have a nonlinear load like this one here. And so the transistor and the load then agree on a point where, of course, the current that flows through the transistor must be the same as the current that flows through the load. This is in general a nonlinear situation. So you cannot easily do this analytically, but graphically it's clear that the point where these curves intersect is then the operating point. And because this curve is so steep, you will always get a voltage here that is roughly 0.7 volts below the reference voltage. So you can come in here with a reference voltage of, in this case, 2.7 volts. And then it's almost independent of what your load does. The point where this emitter ends up is always roughly 0.7 volts below this reference. And this can also be then used as a regulator. So you don't need the feedback through the amplifier here, but in fact, the fact that the transistor really references the current by looking at the emitter and the base acts as a feedback in some sense as well, and keeps this voltage always roughly 0.7 volts below the reference, below the base. And a simple way to use it is, for instance, shown here. Maybe remember last week we used the Zener diode to create a constant voltage for a load. Now here's the improved version, where we don't use the output of this circuit, the resistor plus the Zener voltage, to drive directly the load, but instead we drive a transistor base and then hook the load to the emitter of this point of this. We hook the load to the emitter of the transistor, and now again the steepness of the IV curve of the transistor fixes this potential to roughly 0.7 volts below the Zener voltage for any type of load that we put here. But now we have a very small base current, because the base current here is only a factor 1 over beta of the total current here, which means that the resistor in this circuit can be much larger than it would be when we do this without the transistor, which was, if you remember, the disadvantage of the circuit, that you may have to drop a lot of power through this resistor when you go away when the input voltage goes away from the Zener voltage, and this becomes very inefficient. But now in this way, the current through the resistor can be much, much smaller, and the whole circuit is much more efficient. And the applications are, of course, the same. So you regulate a voltage that is too high or varying, like a battery output, for instance, or you can use it also to reduce ripple in your supply voltage. For instance, when you have a rectifier output, this is not perfectly flat, as we've seen, but it has some residual ripple on it that we can reduce by using such a regulator here. Okay, generally, transistor circuits are typically classified by which of the nodes is at a common potential, at a constant potential. We've just seen one where the base was at a constant potential, or a fixed potential, and these we've also seen one where the collector is at a common potential. So these are, according to that, called either common collector circuits or common emitter circuits or common base circuits. This is not very important. There are, in fact, also interesting circuits where more than one terminal is not fixed. But this is the usual nomenclature, and we'll start by looking at this. We'll start by looking at the common collector configuration here, where we connect the collector to a fixed supply voltage and connect the load to the emitter here. And then we vary the input, and that'll be the so-called emitter follower. And that is shown here. It's a similar configuration to the regulator, but now we use not an arbitrary load, but we put a resistor here. This is the emitter resistor, RE. The input is usually not a fixed voltage, but it's variable, so we will change this voltage and see what happens at the output. So the principle of operation of the circuit is the following. The base is your input, and the emitter is your output. And the base emitter voltage is the difference between the two voltage. And then again, because the steepness of the IV curve, the base current, and hence the collector current, rises very steeply if your base emitter voltage goes above 0.7 volts. The emitter current is more or less proportional to this current, which means that this load here will then produce a larger voltage drop when the current goes up, and that pushes up this point again. So this in turn reduces the base emitter voltage, and we find an equilibrium here. So the base emitter diode regulates this current until we have the configuration where the collector current is the output voltage divided by the emitter resistance. So this means that the emitter or the output will always follow the base, right? With this difference of 0.7 volts, and that's why this circuit is called the emitter follower, because the emitter follows the base. Let's see what this is in terms of IV curves. Now we have here again the same picture as before, where we had a fixed regulator voltage of 2.5 volts. Now we have, instead of different load curves, we have a single resistor curve here, which fixes the emitter current as the output voltage divided by R, or you can also view it the other way around. It fixes the output voltage as being R times the emitter current. And where these two lines intersect, this is where the output will be as a function of the input. So if this is the input, then you'll be here roughly 0.7 volts below. Now, if you change the input voltage, this curve moves to the left accordingly. And then the intercept goes here, and we're again roughly 0.7 volts below the input voltage. And this shift remains constant unless you go to very, very small currents, where you start then falling into this point where the steepness of the IV curve becomes smaller. But as long as you're in this region here, then you have a nice following behavior. So the output voltage will follow the input voltage. So now this is as a SPICE simulation. We have one voltage source here for the supply voltage. We have another voltage source which we're going to vary for the input voltage. There's this standard NPN transistor here, and a 100 ohm resistor to ground as the emitter resistor. And now if you plot the input resistor, it's obviously just the same as we have here on this axis. If you look at the output voltage now, you can see that nothing happens when the output voltage is less than 0.7 volts or so, because then the base emitter diode is off. There's no current here, so there's also no collector current. Once you reach the 0.7 volt, the transistor starts conducting, and the emitter follows the base. So this will only ever work if your input voltage is larger than these 0.7 or 0.6 or 0.7 volts. If you look very closely, you will also see that the slope is not exactly 1, and we'll come back to that in a minute. You can not only make the emitter follow with the NPN transistor, as we've done before. So here, this is the NPN emitter follower. The output follows the input by 1 base emitter drop, these 0.7 volts. You can also make a follower with an PNP transistor. Now you have to put the load again to the emitter, which is now above the base. So this is now the controlling voltage here, the base emitter voltage, or emitter base, strictly speaking. And it's now 0.7 volts higher than the input voltage. So while this circuit will only work when the input voltage is higher than 0.7 volts, this will only work when the input voltage is less than the supply voltage minus 0.7 volt. But you can go down to 0. So depending on what you need to do, whether you need to be able to go down to ground, then you should better use a PNP follower. But if you can afford to, if you need to go higher and can afford to lose some dynamic range here at the bottom, you can use the NPN follower. In both cases, the trick here is again that the base current is much smaller than the collector current, than the emitter current. So the signal source that drives this load needs to provide much less current than the load consumes. So you can have a relatively weak voltage source here, and it can create a robust signal that can be loaded with relatively high, relatively low impedances. So such a circuit is called a buffer. When you it basically allows you to separate the input from the output, so there will be no feedback from the output back into the input. Okay. Now to analyze this in more detail, one usually resorts to so-called small signal analysis. If you always want to do the full analysis, you need to do either SPICE or you need to solve these nonlinear equations involving exponential functions. But we often only want to know what happens around a working point when we change a voltage by a little bit. And so for this, one resorts to a linearized treatment of small signals around a working point. So for instance, we take this emitter follower here, and we define some working point, V in 0, and only look at small deviations from it, which we then call V in with a lowercase v. This will then result in a current that is the working point current plus a small current change. So this is here symbolized by these voltage sources. So you take a DC voltage source, and on top of that a variable input which creates a signal, and you only care about what happens at the output. And you, of course, when this small change is 0, then you will get a DC voltage here, the output 0 for the working point, which is only a function of the input voltage for the working point. And when you add a small change of the input here, you get a small change of the output, which is then somehow proportional to this input voltage change. And since we are talking about small changes, we can linearize the characteristics of our devices. So in this case of the transistor, so when our input voltage when our input current is I0 plus little I, then the output will be like the transfer function. The transfer function of the current plus the slope of the transfer function at that point multiplied by the change of the current, and the same for the same expressed in terms of this small signal voltage here, is that V0 plus little v is the same as the voltage at the working point plus, and then this derivative is called a differential resistance multiplied by this current change. So what we do here is we split the determination of the working point. So where is the voltage as a function of a current, and the small signal analysis, so what happens at this working point when we make small changes of the currents or the voltages. So then to characterize a device, one needs these small signal parameters, which are, for instance, the differential resistance, so the derivative of the voltage across a device divided by the current flowing through it. So it's not just the ratio, which would be for a real resistor, but it's the derivative, because this is typically nonlinear, as we've seen, for instance, for the diode. So this becomes a function of the working point then. The inverse of a resistance is often used, and it's called a conductance. So this is then, of course, simply the derivative of the current with respect to the voltage. And when you have something like a transistor, which is a 3-terminal device, you sometimes relate currents and voltages at different terminals. So here, for instance, the collector current change is given by the change of the base emitter voltage and the change of the collector emitter voltage. And such a conductance, which is then the derivative with respect to the voltage at a different terminal, is called a transconductance. So the most prominent example is called GM, and is derivative of the collector current with respect to the base emitter voltage. So it sort of says how much do we amplify a current through the device by changing a little bit the potential at the controlling gate. Okay, so this transconductance is a very important quantity. It describes the current modulation by the input voltage. And we'll look at this only in the active region where it makes sense. And we'll also just use the domain where the base emitter voltage is much larger than the thermal voltage, so we can simply treat the IV curve as this exponential here. We can neglect the -1 term and everything else. So GM is this derivative, and if we use this transistor characteristic, so collector current is current gain times some saturation current multiplied by the VBE divided exponential of VBE divided by VT. Then we take this derivative. You find that GM is 1 over VT from this derivative here, multiplied by the same factor again. So it's simply the GM is the collector current divided by the thermal voltage. Now this obviously is working point dependent because the collector current is a function of the working point. The interesting part here is that this is a relatively large value. So for a typical transistor current is 10 milliamps or 100 milliamps or so, and the thermal voltage at room temperature is 25 millivolts. So in this case, you get, for instance, 400 millisiemens, which is a relatively large value for a transistor. So it's much higher than what you get for typical MOSFETs. So this makes bipolar transistors interesting for some applications where you need a high GM. Another small signal parameter that is often used is the emitter resistance. So it describes how the emitter potential changes when we have a current change, while we keep the other potentials fixed. So you keep the collector and the base potential fixed, and you vary the current here. So the question is, how does my emitter voltage change? So we have the derivative of the emitter potential with respect to the emitter current at constant voltage, and for this circuit here, and then for the transistor, this is just the derivative of the VBE by the emitter current. Now the emitter voltage is the difference. The emitter voltage. So yes, we get this because the emitter voltage is the difference between the base emitter voltage and the base potential. So that's why we have this here, and we get rid of the minus sign here. Okay, now since the emitter current is the sum of the base current plus the collector current, so this is beta times, so this is 1 plus beta times the base current plus times beta. So we get a factor 1 plus beta here when we take the derivative with respect to the base current instead of the emitter current. And if we want to now express it in terms of the collector current, we have a beta divided by beta plus 1 here up front. And the term that is here, we've already seen on the previous page, is nothing but 1 over GM. So this term for large beta is usually close to 1. So we are simply left with an emitter resistor that is approximately equal to 1 over GM. So GM was collector current divided by VT. So 1 over GM is VT divided by the collector current. And this can be expressed in normal units as 25 ohms divided by the collector current. So this is the resistance that a load would apparently see at the output of a transistor terminal in terms of a small signal, of course. So only when you make small changes, then the output of a resistor will look, the output of a transistor will look like a small resistor of 25 ohms divided by the collector current. So if you have a collector current of 10 milliamps, that's only 2.5 ohms. So you have a very small resistance. This is another way of saying that the emitter potential is relatively constant and independent of what you do, because most loads that you apply will have a much larger resistance than 2.5 ohms. Okay. Now we have what we need to analyze the voltage gain of an emitter follower. So by voltage gain for the circuit, we mean how does the output voltage change as a function of the input voltage. So it's this derivative here. We use the fact that the controlling voltage, VBE, is the difference of input minus output voltage, and that the output voltage is the emitter resistance multiplied by the emitter current. Now, if we take this differential here, output by input, then we get the derivative of the emitter current by the input voltage, which we can write as this product here, the chain, using the chain rule, the differential of the emitter current by the base emitter voltage, and here we have the differential of the derivative of the base emitter voltage with respect to the input voltage, just the chain rule. This we had on the previous page is simply 1 over the emitter resistance, and this is, using this identity here, 1 minus the derivative of the output voltage with respect to the input voltage, which is the amplification that we're looking for. So we have the same term here. Multiplying this by this expression by RE gets us, and dividing by the emitter resistance here, gives us this here. There's the ratio of the resistance. Then there's the voltage gain here, which is equal to 1 minus the voltage gain here, which is this term, of course. And so this is A. So we rearrange terms, and then we find that A is 1 divided by 1 plus this ratio of the resistances. And since the output resistance of the emitter, little RE, is usually a very, very small number, this here is approximately 1, but it's always slightly less than 1. Okay, so this is a small positive number. So the output resistance is close to 1, but slightly less than 1. Okay, so if you look at this term here, this factor looks a bit like the a voltage divider between a between the little RE and the large RE. As you can see here, if you multiply both terms with RE, you get this here, which is the exact expression that you have for a voltage divider. So the output voltage here depends on the input voltage as if there was a voltage divider here. This, however, is true only in a small signal sense. So it does not apply to the working point. If you want to find the working point, you really need to go through the full nonlinear curve. But if you want to do a small signal analysis, so you want to see what happens in this little circle here, in this little circle, when you move this curve a little bit, how does my output change? Then you can replace the whole transistor with a simple resistor between the input voltage and the emitter, and the value of this is this RE, which is the collective divided by the GM. So in the circle, we approximate these nonlinear curves simply by straight lines, and then to find this change itself, we don't really need to know where we are. We only need the slopes. You can convince yourself if you look at this. This is simply geometry, so you can do this without actually analyzing any circuit. And if you just have the two slopes of the two curves, you can find out how the input voltage changes with the output voltage. It's not so important because we will, of course, always use these equivalent circuits. But the message here is that in this approximation, a straight line is a straight line. It doesn't matter whether it's an actual straight line from a resistor or it's just a linearized version of a nonlinear IV curve. The behavior is the same. So whenever we have an amplifier that is some real complicated object, like this one here, where you have an input voltage and an input current that are somehow related, and an output voltage and an output current, we can always replace that in a small signal sense by an ideal amplifier that has no currents at the input, and replace the input current or describe the input current by an input resistor, and we can replace the output, the non-ideal behavior of the output, by adding an output resistor here. And we just calculated the output resistance for the emitter follower amplifier here. Yeah, so R in and R out are simply derivatives of the characteristics of a real amplifier. They are not necessarily actual resistors. Some amplifiers do have real resistors here. For instance, if you want to protect your output against users who short circuit the output, for instance, then you may actually put a real resistor here to protect this device from short circuiting it here. But in most cases, when you talk about an output resistor of an amplifier, it's just a derivative of some IV curve and not an actual resistor. Okay, so far we've looked at the emitter follower in DC mode and we've seen how we can describe some aspects of it using these equivalent circuits, using equivalent circuit parameters, representing them as small resistors. Now we will see that this can also be used for time dependent analysis, so for a transient analysis of a circuit. We've seen that the output voltage as a function of the input voltage in the small signal sense is given by this voltage divider behavior. This, of course, is not this simple resistor is, of course, not a full equivalent circuit. We'll later see real equivalent circuits that describe all aspects of a transistor. This one describes only the input, only the output, and not, for instance, the collector or what happens at the base. But we can use it for this. So this is helpful not only for the DC analysis, but also to model the transient behavior. And if you look at this circuit here, and you have an emitter follower, and you put some capacitance at the output, you expect some RC type behavior. And this equivalent circuit here suggests that the characteristic time constant of the circuit is given by the capacitor multiplied by the parallel value of these two resistors. And this is, in fact, a value that is typically much slower than this resistor itself. So it suggests that such a circuit here, where you have a transistor here, is much faster than just the RC time given by, by the load resistor itself. So let's take a look at that. We simulated here an emitter follower. Now we have a resistor here of 1 kilo ohm, the same transistor here. We have a 1 nanofarad load, which is a relatively large capacitor. And we simulated not in DC, but in time. And if we apply a small signal change here, the input, this is the input voltage varying between 1 volt and 1.1 volt, we see that the output follows the input nicely and very fast, but shifted down by 0.7 volts. Now, if you increase the amplitude of the input, and this is what we're doing here, now we're going and we're shifting it, so we're going between 1 volt and 0.5 volt, then the picture changes a bit, which is of course due to the fact that at below 0.7 volt the transistor doesn't really work anymore. So now what we see is it rises very quickly, but it falls very slowly. And this is now here the behavior that you get when the transistor cannot work anymore. Then the discharge of this capacitor is only through the 1 kilo ohm resistor, and you get a very slow fall time here. So again, this is the small signal behavior. You get very, very fast rise and fall times here, which are much smaller than the microsecond that you would expect. And we get, which is also important, the same rise and fall times. Now, if you look at the equivalent circuit, that's not surprising that you get the same rise time and the same fall time. But if you think of it in terms of a transistor, then you have to think for a minute why this is so. If you do the same for the large signal amplitude, you see the same fast rise time. This is where the transistor pulls up the load. So you come out of a situation where the transistor is off, then you raise the input voltage, and then the current through the transistor pulls up this point here by sending a current through the resistor and into the capacitor. And this goes very fast because the transistor is powerful. But here you go down, the transistor switches off, and the capacitor discharges through this resistor with this relatively slow fall time. Now, the thing that you might wonder about now is why can the signal be so fast when the signal is when the amplitude is small? After all, the current sign at the output of the transistor cannot change. So this transistor can only send current in one direction, so it can only source current. It can never sink current. So why can you have a fast fall time when you need to bring the current down? When you bring the output voltage down, you will somehow need to suck the charge out of the capacitor, but the transistor cannot actually do that. So you may wonder why you see this behavior that you would expect in the large signal case, but not in a small signal case. And we'll try to look at this now by comparing two different cases. So here we model the transistor simply as a switched current source, which is roughly the behavior that we'll have in the large signal case. So the voltage at this point is given by the voltage drop across the load resistor. So it's R times this current, and this current is the difference of the current that we create in the current source minus the current that goes into the capacitance, and that is the capacitance multiplied by the time derivative of the voltage. So this is what we have here. So voltage is R times this difference here. And this can be written in this form. So we have voltage plus RC times derivative of the voltage is equal to R times the current. And this RC is the time constant. And then we have this usual differential equation from the RC filter. Now, if your current is this step function, so you start with some value and then you drop it down to a second value, you can simply solve it for this time here as this sum of exponentials, and the result can simply be written as V2, which is the second the value that you reach for the voltage I2. So R times I2 is V2, and then the difference of the two multiplied by this decaying exponential, which decays with the time constant RC. So this is shown here. This is your input current, makes a step, and then here you see this exponential decay of the voltage slowly reaching the asymptotic value. And this is exactly the behavior that we see for the large signal. When the transistor turns off, the capacitor discharges just through the resistor. Now instead we look at the small signal picture or the actual transistor. So we have the same differential equation here. So the voltage is voltage plus RC times derivative of the voltage is resistance times the current. But this time the current is controlled by the base emitter voltage, and it's not just a step function. So what we change as a step function is the input voltage to the base. So the base emitter voltage now becomes time dependent. It's the difference between the base potential shown here minus the voltage at the output. And because it's a transistor, we can write the current as the current at the working point plus now we use the small signal parameter Gm times this voltage difference, the base emitter voltage. Is this missing? Okay. So for a time greater than 0, this unfortunately a little mixed up here. So we can now go into this domain here. We have the voltage VB2. We can write this equation now as voltage plus RC times differential of derivative of the voltage is R0 times R times I0 plus R times GM times this difference here. Then we separate everything that depends on time, goes to the left-hand side. So now we have the voltage times this factor here. So it's the 1 from this term and the RGM from this term here. And this one is the same, and we're left with these constant terms here. Dividing by 1 plus RGM, this factor here, we get the same equation now. Voltage plus this term multiplied by the derivative voltage is a constant. So now our time constant is equal to tau, is equal to this expression and not RC. So we do get a different time constant for the transistor case. And since GM is equal to 1 over RE, we can write this as RC divided by 1 plus R over RE. So this is the same expression here. Now this is C multiplied by the parallel configuration of R and RE. So this is the same expression that you would in fact expect from the small signal model. So and it's much faster than we got for the current source. So first of all, it shows us that even if we do this in detail, we get the correct result. So the small signal approach is really applicable, also in the time domain. Now we still have to answer the question: how is it possible that the transistor can be faster than the current source when it really is a current source and cannot absorb any currents? So to do that, you have to compare the emitter currents for the two cases. So in one case, we have a current step that goes from one value to the next one. And in the transistor case, we have a jump in the base potential from one value to the other. If you want to know what the current does, you take the output voltage here in the transistor case and use the equation that we had for the differential equation. So the current is given by 1 over R times the voltage, which is the current through the resistor, and this is the current through the capacitor. So you need the derivative of this. So here we have simply V2 divided by R plus the difference here, V1 minus V2 divided by R and the exponential, and then the C times the derivative, which is this term here. So you get a minus 1 divided by the term that you have here with the same exponential. If you rearrange the terms a little bit, then you get this formula here, which is no longer a step function, but it's a quite different function. And if you look at it, it's plotted here. So for the current source that we simply switch off, you get this step here. But if you do the transistor, it dips down much below the asymptotic value. So in some sense, it cannot sink the current, but the differential current can go negative. So the output current is still positive, but it's much less than the asymptotic value. So in a differential value, it really does become negative. And in this way, the transistor circuit can discharge the capacitor much faster than the simple RC curve. So here you get the RC behavior, which is much slower, and here you are faster because you initially drop much below the asymptotic value. So, but this of course only works when this dip here does not need to go really into the negative, which of course it can't. If you get into a situation where the dip would go into the negative here, then it cuts off because it cannot actually go negative, and you get this slow behavior here. Okay. so much for the emitter follower. I think I hope I convinced you that we can describe it by this small signal equivalent circuit, and that works for DC and for AC. Now let's look at a variation of this, which is the so-called push-pull follower. Let's start with an NPN emitter follower. We again have the problem that the transistor cannot sink any current from the load. So if we have a load here and we want to go negative, then the transistor cannot absorb this current, but all the current has to go through this resistor. Now if we want to turn off a load for very large voltage swings and not for small signals, as we've discussed before, but you really want to go into this domain here where you want to go down to 0, but not become slow, then you would need to make this resistor very, very small if you want to make this fast. And a very small resistor is of course unwanted, because then your emitter follower always draws a lot of current. So the solution is to replace this resistor by another transistor, in this case a PNP transistor, and this one is then this one can now pull the point down as well, and this configuration is called a push-pull follower, because it can push and pull the load in both directions. So this one acts as a follower, and this one acts as a follower, and the other one is the emitter resistor for the other. So each one is a emitter follower, emitter resistor, sorry, for the other one. There's another configuration that looks almost the same, but where you exchange the P and N transistors. So you really have to look carefully here. When you exchange P and N transistors, it's not a push-pull follower, but a so-called inverter. Just to warn you, when you see this arrangement of transistors, you have to look carefully where the P and where the N is. So here the N transistor is at the top and the P is at the bottom. If you do it the other way around, you don't have a push-pull follower, but the inverter. The push-pull follower, as it's shown here, is a so-called Class B amplifier. The problem is here that only one transistor is active at a time, and there's a region in between where none of them does anything. And this is given by the range where the base emitter voltage is less than 0.7 volt in either direction. And here you have no amplification, and this is called a crossover distortion. So when you come in with a true sine wave here, then the output will need a little offset to follow this 0.7 volts, but this offset changes sign when you go through 0. So there is a region where it doesn't work, and this crossover, this is called crossover distortion. This can be compensated by adding diodes here. And then you make sure that the base voltage here is always one diode voltage above the input voltage, and then you have to put a bit of current through this diode to make sure that this is actually the case. But then this base will always follow the input, shift it up by 0.7 volts, and then you avoid the crossover distortion. And this kind of output is very often used in power amplifiers or operational amplifiers. So we will see that later when we look at an operational amplifier. They sometimes use this as an output stage. So this is it for today. Okay. Are there any questions? No? Okay. Okay, so see you next week then.